Hi all, for this video we're working with the standard for trigonometric identities. Our objectives include fundamental identities, Pythagorean identities, sum and difference identities, double angle identities, and half angle identities. We'll repeat a few things we did with like the right triangle trig or unit circle definitions, and then we'll build into the bigger identities and show you how to use them a little bit. So we start with fundamental identities and a definition. An identity is an equation that is satisfied by every value in the domain of its variable. Recall, we have the following definitions for the trig functions. So sine of theta was y. Cosecant theta then was 1 over y. Cosine was x. Secant was 1 over x. Tangent theta was y over x, and cotangent theta was x over y. The reciprocal and quotient identities follow from those definitions. Right, for sine then, we had 1 over cosecant theta for our reciprocal. And likewise, cosecant theta would be equal to 1 over sine theta. Cosine theta would be 1 over secant theta. And secant theta is equal to 1 over cosine theta. Tangent theta would be equal to 1 over cotangent theta. And cotangent theta equal to 1 over tan theta. So those are all our reciprocal identities. For the quotient, tan theta is the y over x. You can see is sine theta over cosine theta. And as its reciprocal, cotangent theta is x over y, or cosine theta over sine theta. So hopefully we remember those kind of base definitions we have and we've been working with. From there, we talked about the cofunction identities a little bit before. And I won't write out maybe everything here, but at least to explore a couple. This sine of pi over 2 minus theta, if we look from that angle, our sine is our opposite over hypotenuse, so we'd get an x over r. We also want to look at that from angle u. And so from angle u, x over r is our adjacent over hypotenuse. So that's our cosine of u. All right, and we're going to see the same thing as we go through all of them. Cosine of pi over 2 minus u. And maybe we can look at a couple more. Adjacent over hypotenuse would be y over r here. That's equal to, if we look from u, our opposite over hypotenuse, so our sine of u. And we can do the same thing going down with the other cofunctions. Tangent of pi over 2 minus theta, opposite over adjacent is an x over y here. That'd be the same as cotangent of u, right? Our adjacent over opposite. Cotangent of pi over 2 minus u. Now we've got our adjacent y over opposite x. That's going to be the same as tangent of u, right? From u, y is our opposite and x is our adjacent. And the same thing for the last two cofunctions. Secant of pi over 2 minus u is equal to cosecant of u. And cosecant of pi over 2 minus u is the same as secant of u. So we're looking at just those other two angles in that right triangle. They together add to 90. We'll have these nice cofunction identities that come from them. For 1 then, we have if sine of 3 pi over 8 equals a, then what does cosine of pi over 8 equal? So what we want to notice based on those cofunction identities is that pi over 2 minus 3 pi over 8 is 4 pi over 8 minus 3 pi over 8, which is pi over 8. So together these two would add to 90, or to pi over 2 radians. And so what we get from that cofunction identity, sine of 3 pi over 8 is equal to cosine of pi over 2 minus 3 pi over 8, which is cosine of pi over 8. And since it's equivalent to sine of 3 pi over 8, this value is also a. All right, so we can use those cofunction identities to find the cofunction values if our angles add to 90 or add to pi over 2. For the Pythagorean identities, we want to start back with that unit circle. So based on the definitions of sine and cosine and their relationship to the unit circle, we get the following result. We have, of course, that our unit circle was x squared plus y squared equals 1. Right, center 0, 0, radius 1. From our definitions, Sometimes you'll see this written sine squared plus cosine squared, but if we're subbing in for x, we've got cosine squared theta. For y, we've got sine squared theta. If we add those together, we should still get 1. So that's our Pythagorean identity. We can manipulate that to get a couple other ones. So if we start with our base identity, the cosine squared theta plus sine squared theta equals 1. If I divide every term, or both sides of my equation, by cosine squared theta, right, so I'm dividing the whole side by dividing every term by the value. I have for my identities above, cosine squared theta divided by itself is just 1, but sine squared theta over cosine squared theta is tan squared theta, and 1 over cosine squared theta is secant squared theta. So we get 1 plus tan squared theta equals secant squared theta. If we divide by sine squared theta instead, so I'll start again with cosine squared plus sine squared theta equals 1, and this time we'll divide by sine squared theta everywhere. We can get an identity that involves cotangent and cosecant. So we're dividing both sides, or every term, by sine squared theta. Cosine squared theta over sine squared theta would give us cotangent squared theta. Sine squared theta divided by itself gives us the plus 1 there, and 1 over sine squared theta is cosecant squared theta. So we'll have Pythagorean identities involving all the 6 trig functions, all with the function squared. That'll come up later when we are solving some equations. So we want to keep these in mind, and we also want to take note of the fact that we can manipulate them as well. So I could say solve for cosine and get 1 minus sine squared theta, or cosine squared theta equals 1 minus sine squared theta. I could get cotangent squared theta equals cosecant squared theta minus 1. So we can manipulate these to do some substitutions when we need to. All right, for the sum and difference identities, there are proofs for them. You could look them up if you want to. I think they're a little more in depth than what we're doing, I guess. But if we do know these, we can derive the rest from them. So this is kind of the stuff you would need to maybe memorize, have one of these known. What we do want to take note of is that cosine of a plus b is not the same as cosine of a plus cosine of b. If we look at something like cosine of 30 degrees plus 60 degrees, that's the same as cosine of 90 degrees, which we know is 0. But if we take those separately, cosine of 30 degrees plus cosine of 60 degrees, from our unit circle values, we get a root 3 over 2 plus 1/2, which is very clearly not 0. All right, so we do have to have some identities, some values that will work for every a and every b, or every angle here. So for cosine of a plus b, I don't know if there's an easy way to remember it, but for cosine, we're going to have cosine of the first angle times cosine of the second angle. We get a sign change in the middle, so minus, then sine of the first angle times sine of the second angle. And for the minus, we'll just get a plus in the middle there. So it still starts with cosine A, cosine B, but we'll get a plus sine A, sine B. We haven't talked about even and odd functions yet. There's a little proof there to show why we get that sign change for the second one. But it just comes from the fact that sine is an odd function. Cosine's an even function. We'll talk about symmetry and even odd later in the course, but if we start with these two, we can kind of do the rest. So if we have something like cosine of 13 pi over 12 here, that's not a unit circle value, we can use these identities to figure out an exact value for it. We can break the 13 pi over 12 up by adding together 9 pi over 12 and 4 pi over 12. If we reduce those, we get a 3 pi over 4, not comma, but plus a pi over 3. So we've reduced it to a couple unit circle values that we can evaluate and find an answer here, right, to simplify or evaluate this cosine of 13 pi over 12. So using our identity, we get cosine of the first angle, 3 pi over 4, times cosine of the second angle, pi over 3. Since we've got a plus inside, we're going to do a minus sine of the first angle, 3 pi over 4, times sine of the second angle, pi over 3. And then we just want to get those values from our unit circle. You can pull it out. You can draw some triangles if you need to. But anything over 4 is a root 2 over 2 for sine and cosine. Since we're in quadrant 2, cosine is going to be negative. So we get a negative square root of 2 over 2. For the pi over 3, we get those 1/2 for the cosine. We're in quadrant 1, so just a positive 1/2. And for sine of 3 pi over 4, y would be positive in quadrant 2. So we get a positive root 2 over 2. Times, for pi over 3, we get that root 3 over 2, since cosine was the 1/2. We can multiply those out and then simplify a little bit if we can. We get a minus the square root of 2 over 4 minus square root of 6 over 4. And usually we'll put those together as a single fraction. So minus root 2 minus root 6 all over 4. So that would be our exact value for cosine of 13 pi over 12. As the note says here, we can use the cofunction identities to find the identity for sine of a plus b. So from our cofunctions, we have that sine of a plus b is the same as cosine of pi over 2 minus a plus b. And we can rearrange that inside to take a cosine of pi over 2 minus a minus b. So we can think of that pi over 2 minus a as our first angle, and the minus b as our second. So we're working with our cosine of a difference from the last page. And so this would be equal to cosine of pi over 2 minus a times cosine of b. Since we had a minus in the middle there, we're going to get a plus. Sine of the first angle, pi over 2 minus a, times sine of the second angle, b in this case. And then we'll further use those cofunction identities to rewrite this. That cosine of pi over 2 minus a would be the same as sine of a times cosine of b then, plus cosine of a, right, cofunction for the sine of pi over 2 minus a, and then times sine of b. So we've got our first sum or difference there. The sine of a plus b gives us a sine a times cosine b plus cosine a times sine b. And so for sine, we can see that the sign stays the same. Maybe a circle instead of putting a minus there, or underline, but we want to see that sine stays the same, but the sine and cosine swap. So sine a cosine b plus cosine a sine b. And what we'll see for the second identity is that those values stay in the same order, sine a cosine b, but we'd get a minus cosine a sine b. And again, that one's going to come from symmetry. You can look it up if you want to, or trust me. So we're going to use them. I think I meant to take one of these out, but they're both here, so let's do both. For sine of pi over 12, we can rewrite that with sine of pi over 3 minus pi over 4. Again, we just want to find unit circle values that have a sum or difference of the angle we're evaluating, so we can find all our values from the unit circle. Using our identity from above, this is going to be equivalent to sine of pi over 3 times cosine of pi over 4. Sine stays the same, so we get a minus cosine of that first angle, pi over 3, times sine of the second angle, pi over 4. And then we can take our unit circle values. Sine of pi over 3 is the root 3 over 2. Pi over 4 is a root 2 over 2 for both. We're in the first quadrant, so everything's positive. Minus cosine pi over 3 is then the 1/2, and pi over 4 is our root 2 over 2. So when we multiply those out, we can see both will be over 4. So I can save some space in a step here. Root 3 times root 2 would give me a square root of 6, minus the square root of 2 all over 4. For tangent, you'll notice we didn't write a formula there. There are formulas you can memorize if you want to, but really we just want to go back to the fact that tangent is equal to sine over cosine. And so for this one, we're going to do sine of, I got it here, pi over 6 plus pi over 4. divided by cosine of pi over 6 plus pi over 4. Right, so again, we've got two unit circle values that add to 5 pi over 12, and we know tangent is equivalent to sine of the angle over cosine of the angle. So we want to run these through our identities. The numerator, we just did a sine of a difference over there, so sine of a sum would be sine of the first, pi over 6 in this case, cosine of the second, pi over 4. Sine stays the same, plus cosine of the first, pi over 6, sine of pi over 4, all divided by, for cosine, we had cosine of the first, pi over 6, times cosine of the second, pi over 4. We get that sign change here, so minus sine of pi over 6 times sine of pi over 4. And we just want to sub all those values in. So I'm going to go down here. Sine of pi over 6 was the 1/2. Cosine pi over 4, root 2 over 2, plus cosine pi over 6 is the root 3 over 2. Sine pi over 4, again, root 2 over 2. And for my denominator, cosine pi over 6, the root 3 over 2, times cosine pi over 4, the root 2 over 2, minus sine pi over 6 is my 1/2, times sine pi over 4, my root 2 over 2. And so if I multiply all these out, I get a rad 2 plus rad 6 over 4, all divided by rad 6 minus rad 2 over 4. If I do that fraction division, I'm multiplying by a reciprocal. Really, those 4's are going to divide out. And just like we've done before for sine divided by cosine, we get the numerator of the top, root 2 plus root 6, over the numerator of the bottom, root 6 minus root 2. Feel free to write out that step if you want to. If you want to go further, you can rationalize the denominator here too, but that's good. It's a nice exact answer. For the double angle identities, we're going to use the sum and difference identities to derive the double angle identities for sine and cosine. We can start by thinking of cosine of 2a, our double angle, as cosine of a plus a. Just to differentiate, we can use a color here. So we get from that identity cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. But since those angles are both a, we end up just with cosine squared a minus sine squared a. So we can put that one in for one of our double angle identities for cosine 2a. We get cosine squared a minus sine squared a. Our other two are going to come from Pythagorean identities, or really that base Pythagorean identity. We had that cosine squared, we can do a plus sine squared a was 1. If we solve for cosine, as I mentioned but didn't do because we were going to do it here, cosine squared a is equal to 1 minus sine squared a. Or if we solve for sine, we have that sine squared a is equal to 1 minus cosine squared a. So we'll do one at a time. I'm going to substitute 1 minus sine squared a in for cosine a first. And so we have that cosine of 2a is equal to cosine squared a minus sine squared a. But if we're subbing in for cosine, we get or cosine squared, we get a 1 minus sine squared a minus sine squared a. I have 2 sine squared a's, so this becomes a 1 minus 2 sine squared a. So we can put that for another identity here. 1 minus 2 sine squared a. And we can do the same thing with the other solve there from that fundamental Pythagorean identity. Cosine of 2a is equal to, again, cosine squared a minus sine squared a. If we do our substitution for sine squared a this time, which was equal to 1 minus cosine squared a, we would have a cosine squared a minus our quantity of 1 minus cosine squared a. If I distribute that negative, I get a cosine squared A minus 1 plus cosine squared A. Add my like terms, gives me a 2 cosine squared A minus 1. So that's my third identity for cosine 2A, 2 cosine squared A minus 1. And for sine 2A, we can go back to kind of what we did for cosine 2A at the top. Sine of 2A is equal to sine of A plus A. And we can use our identity for sine. We get sine of the first angle, let me bring the color back again, times cosine of the second angle, but still A. Sine stays the same here, so plus cosine of the first angle times sine of the second angle. And so we can see with that commutative property for multiplication, we have a sine A cosine A for both terms, so we can write them together, and we have 2 of these sine A cosine A terms. So sine of 2A we just have one identity for. It's equal to 2 times sine of A the angle cosine A. All right, and then hopefully we can use those too. But before we use it, let's do some derivation of the half angle identities. So we're going to use 2 different ones. First, that cosine of 2A equals 2 cosine squared A minus 1. And we want to solve for cosine of A here. So our first step, we can add that 1 over, and we get a 1 plus cosine 2A equals 2 cosine squared A. Right, so we added the 1 to both sides. Then we can divide by the 2, which gives us, I'm going to rewrite it this way, cosine squared of A equals 1 plus cosine of 2A all over 2. And then we want to take the square root to solve. So we'd have down here for our half angle identity, cosine of A over 2 is equal to the square root of 1 plus cosine of A all over 2. And so what we want to take note of here, because you can see in the formula we're going to have this A over 2, and then A is just that the angle outside here is half of the angle inside, right? So A over 2 is half of the angle A inside the identity below. And really what we're doing here is taking our square roots. So we have just cosine of A equals plus or minus, we've got that square root 1 plus cosine 2A over 2. And so we can say for the half angle identities, the sign for the square root, right? You may remember the plus or minus when we're solving for an unknown value. The sign for the square root comes from, as with a lot of trig, the quadrant of the angle in question here, which is A over 2. So wherever that angle's located, if it's cosine of 45 over 2 and we get 22.5 or whatever, that'd be in quadrant 1, so it'd be positive. If we get something in quadrant 2 where cosine's negative, we'd get the negative square root. For sine, we can use the other identity that we had for cosine 2A. So cosine 2A equals 1 minus 2 sine squared A. We can now subtract that 1 on both sides, and we can write it as a negative 1 plus cosine 2A equals negative 2 sine squared A. Then divide by our negative 2 everywhere, which is going to change the sign of both of those values on the left. So we can get it to what we'll be familiar seeing, a 1 minus cosine 2A over 2 equals sine squared A. And we can take the square root of both sides and rewrite it in a more familiar way down below. When you look it up, or when you look at it in the notes, you'll see it like this. Sine of A over 2 is equivalent to, we can keep the plus or minus here. We'd have a 1 minus cosine of A over 2. So again, that angle inside is double the angle outside, or the angle outside is half of the one we're using inside. That's our half angle identity. All right, for the problems, we want to note that the sum and difference, double angle, and half angle identities for tangent are used much less frequently, but can be found by dividing the respective sine and cosine identities. So we'll do another one of those here. We want to evaluate these last two and leave our answers in exact form, so no decimal approximations, no calculators. Tangent of pi over 8 would be the same as sine of pi over 8 divided by cosine of pi over 8. So we're going to use those half angle identities. Sine of pi over 8 would be the same as the square root of 1 minus cosine of, you can think of it as 2 times pi over 8, or really double that angle. We'll get pi over 4 right inside, all over 2, divided by our square root of 1 plus cosine of pi over 4, all over 2. When we do divide these, we end up again with just numerator over numerator. You can do the multiply by the reciprocal if you want, but we get a 1 minus cosine pi over 4 over the square root of 1 plus cosine of pi over 4. From our exponent rules, we know we can put those together, but this is going to look funky kind of no matter how we do it, so let's just leave it like that for a sec. Cosine of pi over 4 is going to be the same for both. We know it is a square root of 2 over 2. Right? It's in quadrant 1. All the pi over 4's give us a root 2 over 2. It's going to be positive, though, again, because of that quadrant 1. Same thing with our signs for both of the half angle identities, right? Pi over 8 is in quadrant 1. So tan pi over 8 is positive, right? Greater than 0 here. Same with sine pi over 8, cosine pi over 8, right? All those values are going to be positive, greater than 0. Pi over 8 again is in quadrant 1, where all are positive. We can do a little bit to simplify this. If we want to get a common denominator underneath there, we get a 2 minus root 2 all over 2, divided by our square root here, a 2 plus square root of 2 all over 2. And again, just like we did for the first part and for the sine over cosine a lot in the past, or here I can show the reciprocal if we want to see it one time. Our square root of 2 minus root 2 over 2 times reciprocal of that fraction in the denominator, our square root of 2 over 2 plus rad 2. We could bring those together underneath that same radical because of our exponent rules, right? Both are to the half power, so we can do that power of a quotient, right? A to the n over b to the n is the same as a over b to the n. And then do our multiplication. So we get a square root of, we can keep them all together for our answer, 2 minus root 2 over 2 plus root 2, as those 2's factors in the numerator and denominator divide out. All right, and we can leave it like that. That's a nice exact answer for us. For B, our last one, if sine theta is equal to 3/5 and theta is in quadrant 2, we want to find the value of tan 2 theta. So a few things we need to know. A lot of this, again, as you've seen, goes back to unit circle values, and the other part is the right triangle trig here again. So we want to draw a triangle in quadrant 2. For some angle theta, we know sine of that angle, our opposite over hypotenuse, is 3 over 5, and we need to find our value for x. You might know that it's 4 and negative 4 because we're quadrant 2 at this point. If not, we can do a little bit of scratch to find it. Again, we're back to a Pythagorean identity. Our x squared, or Pythagorean theorem, plus 3 squared is equal to 5 squared. X squared we don't know, but 3 squared is 9, and 5 squared is 25. If I subtract my 9, I find that x squared is 16, and the square root of that is 4. Because I'm in quadrant 2 again, I'm going to get a negative value for x. All right, so then we can find some values. We need to use our identities again. We did another tan one, so we could kind of show you both, sine 2 theta and cosine 2 theta. So tan 2 theta would be equivalent to sine of 2 theta over cosine of 2 theta. Always start with what you know, start with the identities, and then we can build from there. For sine of 2 theta, we only had one identity. It was 2 times sine of theta times cosine of theta. For cosine squared theta, or cosine 2 theta, we can use any of those 3 identities. In general, we want to use the one that involves given information, just in case we made a mistake or did something silly. We were given sine of theta here equal to 3/5. So I'm going to use the identity that involves sine of theta, so 1 minus 2 sine squared theta. And then we just want to plug in the values we get from our triangle. So we have a 2 times sine of theta would be our 3/5. Cosine of theta is our negative 4/5. All over 1 minus 2 times sine theta was 3/5, quantity squared. And then we can simplify. We get a 2 times negative 12 over 25 over a 1 minus 2 times 9/25, which is going to give us a negative 24 over 25 divided by 1 minus 18 over 25, which is negative 24 over 25 divided by 7 over 25, because 1 is the same as 25 over 25. And then again, like we've seen before, we can multiply by that reciprocal, but we'll end up with numerator 24 over numerator 7. So minus 24 over 7 is what we get for our tan 2 theta here. So that's it. Try the ticket, bring some questions.